That's not written.
591B. So
Yeah, that was
not sign it. It's read safe. Yeah. Thanks. 5. I want to go to my site. What number?
1B.
1B. This one?
Yes.
So let's just take a minute and write this up. So 5.9 1b, I have the integral from 0 to 4 of 3x, the square root of 25 minus x squared dx, and it tells you to let u equal 25 minus x squared. So du is minus 2x dx. Okay, I'm going to flip this over. Sorry about that. So I have this, right? I can come in here and multiply by negative 2 and divide by negative 2. So then negative 2x, that's dx, not du. Sorry about that. Getting ahead of myself. So negative 2x dx can be replaced with du. So if I do this, I have a minus 1/2, the integral of 25 to 25 minus 16, so 9.
9.
So then I'm left with the 3, and then I have the square root of u, and then I have du. Okay? So it turns out, you see this negative? So when I integrate this, you would agree from 0 to 4, this is always positive. But when I integrate this, I'm going to have an upper bound minus a lower bound that's larger, so I'm going to get a negative number here. But the negative out front takes care of that to make that positive.
So that's why the answer ends up being a positive 3 over 2 rather than, well, a part of the answer ends up being a positive 3 over 2
So
rather than a negative 3 over 2.
if I follow through here, I have minus 3 over 2, u integral of u to the 1/2 would be u to the 3 over 2 divided by 3 over 2. So 2 there. So the 2's cancel, and then I plug in 9 and 25. So I would have a negative 1 out front. U to the 3 over 2 minus, oh, 9. Sorry, this would be 9 to the 3 over 2 minus 25 to the 3 over 2.
Yeah, it just asks us to set it up in this problem in terms of u, so just up to that.
Yeah, so this would be your answer here.
That wasn't what the book at, was it? Look at the bounds flipped.
And they got rid of the negative then.
Yes.
And that's what I was trying to say with the example here. So it turns out a theorem is if I integrate from a to b of f of x dx, that's going to equal minus the integral from b to a of f of x dx. If you flip your bounds, you're not negate. You take the negative of that integral. Because what we're doing here is we're adding up some area from some a to b. Where if we add up the area from b to a, it's going to be negative. So the negative of that would be the original.
So both answers would have been
Correct.
Okay.
And the book has 1/2 the integral from 9 to 25 of 3 times the square root of u du. And they probably pull out the 3.
Yeah.
But
Yeah,
But
that's
yeah.
just 3 over 2. Yeah.
question.
So is it after evaluating that we should change the bound or before evaluating? Or is to the decision?
You have the two methods. If you're integrating with respect to u and you don't want to go back in terms of x, you need to change your u bounds. If you're saying, I'm going to plan on going back in terms of x, you don't write bounds here, and then once you get it in terms of x, you would write your original x bounds. Because if I have x to be 4, then when I plug that back in terms of x, I'm going to get 9. So I can just leave u to be 9, the upper bound on that. But both ways, any one of these approaches in terms of u will give you the same answer. So you could also write minus 1, 25 minus x squared to the 3 over 2 from 0 to 4.
Put your x back in for u.
Yeah, and then you use your x bounds. So function of x bounds. Function of u bounds. Those are the two methods of a definite integral in terms of using a u substitution. You can say once you did your first step on u substitution, you never have to go back in terms of x as long as you change your bounds in terms of u. Then you're fine. And then you integrate in terms of u and plug in your upper u bound minus your upper or your lower u bound. But if you're just stuck on going back in terms of x, perfectly fine, you can use your original x bounds.
Had it been a positive 1/2
Mm-hmm.
and it was 9 over 25, and we wanted our higher bound to be at the top, then we would change it to negative. Right?
Correct,
Okay,
yes.
so it's kind of interchangeable.
Anytime you change the bounds, you're just making it the whole integral negative. Question? You can leave it with the lower bound greater than the upper bound and leave it negative. So no, you don't have to change it. Question?
The way
Here?
right where your mouse was, just above where your mouse pointer is.
This?
Yeah, I understand that 3/2, that comes from the 3 that was on to the right side of the.
Yeah, this minus 3 over 2. Yes.
And then, however, I'm not certain why you've got a 2 and a 3 there. Did you just flip and multiply?
When so when I integrate u to the 1/2, that's u to the 3 over 2 divided by 3 over 2.
So you just flipped and multiplied the bottom?
Yeah, so
Okay.
anytime I divide by a fraction, I flip that and multiply. So
Okay.
the numerator of the fraction stays in the denominator, and the denominator of the fraction flips up to the numerator.
So then you end up with, -1.
Yes.
Okay, I get it. Thank you.
Question?
Why do you multiply by -2 on the other side if you're not using it?
Here,
No, up one.
here, here.
Yeah, why did you multiply?
From my u, the derivative of u would be minus 2x dx. So I really need a minus 2x dx to replace that with du directly. So if I multiply by -2 here, then I have to divide by -2 out front. So then
But
this,
if I just found dx instead, could I just
You'll
put
get the-
-1/2 in the front?
yes, you'll get the exact same thing, yeah.
Okay.
Yeah, because if you solve for dx, you have du divided by 2x. And then this x is going to cancel with the dx, and then you're going to be left with 3 divided by -2.
Yeah, I don't
which
think
will
the
give the
book
exact
ever
same
shows
thing.
that step where you keep it in terms of, or make it equal du with the -2. And the
It
dx.
doesn't.
They just
They
substitute
don't, yeah.
the fraction.
This book doesn't teach that technique. The Stewart book, which I taught out of at Rolla, had both techniques, and it makes sense that this is a relationship. So if I want to solve for what is dx in terms of du, that's du over minus 2x. So I can just replace this directly with dx and then see how everything cancels out. So you get the exact same thing, because you see that if I plug this in here, my x's are going to cancel, and I'm going to be left with 3 over minus 2, which is exactly what I have here. So the book doesn't really go into detail on this. This is from a different book. I think it makes sense in the case that if you always solve for this, you'll always get this constant to work out nicely. Versus here, sometimes students forget they need to manipulate it to get this in exact form. Or they don't carry it through or something. So I've seen students make less mistakes when they go ahead and solve for dx in terms of du and plug that in. Because then they get that constant right there. Question?
I want to just confirm, I think I understand this pretty well, but because we were anticipating a negative out in front, we intentionally flipped our bounds.
Your book did, yes.
Well,
This would be perfectly correct. If you did this on a quiz or an exam, you get full credit.
Then,
this- is just another way to approach it.
Yeah, absolutely. But I just to make sure that if I were to do that method,
Yes.
I don't have to account for plugging this negative that's like been hanging out over here and
Correct,
everywhere else.
yes.
If I didn't flip the bounds, then I would have to change the sign at the end.
If you
Right.
if you left the bounds here,
Uh-huh.
you would have to account for this minus a half out front. You need to distribute that in.
Okay.
If you flip the bounds, you don't have to worry about distributing a negative.
But then at the very end, the last step, where you take 9 to the 3
Yeah.
half, that sign won't change depending on whether or not you flip your bounds. In between them.
Well, this would be, if I flip my bounds, it's going to be 25 to the 3 over 2 minus 9 to the 3 over 2, and then this wouldn't be negative. It'd be positive. And that would be 25, it would be positive 25 minus 9, which is exactly what I get if I distribute the negative. Make sense?
Yes.
Any other questions on the written homework or on Wiley? 70?
Could you probably do 5.3 number 12?
So 5.3, number 12. And 11, 12. So, is this the correct?
Mm-hmm.
So this is a u substitution. If I plug in u to be 3x, the derivative of that is 3, so I have to deal with the 3 here. But what is this form, this general form? Is it inverse sign?
Yeah. Well, if you take
Inverse secant, right?
Yeah.
Inverse secant in terms of u, and then you have substitute. So you have this, and then what would be b is going to turn out, because the derivative is going to cancel, and you're going to look at inverse tangent. So I believe, let's look at writing, what section was this? 5.3, number 12.
So after you cancel everything out, then you should see where you put in the secant inverse?
It's so let's just write this real quick, and then I have dx divided by x, the square root of 9x squared minus 1. So recall that the derivative with respect to u of secant inverse of u is 1 over u, the square root of u squared minus 1. These are in 3.2, 3.3.
That's, we're only going to have sine inverse and tangent inverse?
Yes.
Okay.
So this is actually the absolute value. So
This is at 3.3.
yeah, this is from
Book.
3.3, and this is page 201. This problem is from 5.3, but recall from 3.3, it gave you the list of all the derivative of the sine inverse, but focus on sine inverse and tangent inverse. Potential to show up on the final exam. But in your homework, more possibilities of other things showing up because you have access to the notes in the book and stuff. So here, if I do a u substitution, then du becomes 3 dx. So if I solve for dx, I have du divided by 3. So I have the integral of, say, 1/3 du divided by, what would this x be in terms of u?
U divided by 3.
Right, because I want to simplify everything. So this is actually not going to be secant inverse. The square root of u squared minus 1.
Did we solve for x over there?
So a fraction divided by a fraction, I flip and multiply. So it turns out the 1/3 cancels with the 3. Oh wait, it will be secant, sorry. So then I'm integrating du divided by u, the square root of u squared minus 1, which by definition is secant inverse of u plus c. And then if I back substitute, I have secant inverse of 3x plus c. Does this have bounds? No? Okay, good.
Is it not the absolute value of 3x? Or is it just...
Don't believe it's the absolute value of 3x. No,
It's not.
I don't think so.
So then for B, it'll be the same thing, probably.
Yeah, so b is going to be similar. It's going to be tangent inverse, though, because when you take the derivative of the square root of x, you get 1/2 x to the minus 1/2. So potentially to c, it might or might not cancel. So let's do this one real quick. I have the integral of dx square root of x 1 plus x, and u equals the square root of x. This is b. So du becomes 1/2 x to the minus 1/2 dx. So if I solve for dx, I have 2 times x to the 1/2. So I have the integral of 2x to the 1/2 divided by x to the 1/2, 1 plus x squared, but if I square both sides here, I have x equals u squared, so I have 1 plus u squared du, so the 1/2 cancels here, and you're integrating to the integral of 1 over 1 plus u squared du, which this is exactly tangent inverse of u. So I have 2 times tangent inverse of the square root of x plus c. So the setup of this thought made you think, oh, I'm going to plug in u here, but you wouldn't plug in u because you have to have the square root of x in the denominator to cancel with the square root of x in the numerator. So then you need to manipulate your relationship between u and x to solve for x by itself to get that in terms of u, and you get exactly tangent inverse. Question?
When you have the dx equals 2 times
Mhm.
x to the 1/2, where's the
du, there should be a du right here. Thank you. Yeah, so if I solve for dx, it would be du multiplied by 2 multiplied by x to the 1/2 to get that to be 1, and that's what I get over there.
It's not du divided by all those.
It is divided by, but when you divide by a fraction, you flip and multiply it. So it's 1 divided by 1/2, which is 2. 1 divided by x to the minus 1/2, which I can bring that to, which would be x to the 1/2. Any other questions?
I had a kind of general one about area between two functions
Mhm.
we were doing yesterday.
Mhm.
When you have a function that's above the x-axis and below,
Mhm.
the other one's below,
Mhm.
then are you actually like adding the inverse of the lower function? Or are you subtracting
No,
the
so
difference?
when you integrate it, you get negative. But when you subtract a negative value, it's positive. So it's actually working out nicely, right? It counts for itself.
Okay.
So yeah, so if I take f of x minus g of x, and if g of x is negative, I'm really taking f of x plus g of
You are
x.
essentially adding.
So you're getting that distance, which is a good concept to think about when we get to 6-2. So if I have, let's look at the area between two curves. If I have f of x, and let's just go ahead and make this g of x, and if I want to integrate that from a to b, I take a height, so I'm finding area. I take a height times a differential dx, right? So if I take the integral from a to b of f of x minus g of x dx, this is the height times the length. That gives me area, right? If I take a height times the width, that gives me area, right? So I'm adding up all these heights, and I'm summing that from A to B, that's going to give me area, right? Do you guys understand that concept? I get area by integrating height from a bound. So this differential length comes in important because how do we get area? We take two measurements multiplied by each other. 6.2 is all about finding volume. So this concept is going to be similar. We're going to find volumes by slicing. We're going to use the disc and washer methods. So let's first just look at the disc method. So if I have a function f of x, let's say I rotate this about the x-axis from the bounds a to b. So if I take this area and I rotate that about the x-axis, would you everyone agree that I would have a volume then? So let's see if I can do this shape here. So I'm going to have some kind of cylinder. Sometimes these come out pretty bad, so sorry. So this is my axis of rotation. So this is x. Then we're doing the exact same thing. When we talked about area, we took slices of height, right? Here, when we talk about volume, we're going to take slices of area. Because to get volume, I have to take an area times a distance or a length to get volume, right? So if I slice this, here, if I take this slice and I rotate this, I get, let's see if I can do this decent. If I take this cross-sectional area, because remember this is a volume, and if I take this cross-sectional area, so I like to always draw my axis of rotation and what a cross-sectional area looks like, and when I do that, I have some differential length delta x. So I'm taking slices perpendicular to these x-axis. So each slice is going to have a differential length delta x. And then the distance from my axis of rotation to the function is just going to be a function of x, right? So how would I find cross-sectional area of this disk? 2 pi r squared, right? But what is my radius? It's a function of x, which is named f of x. So it could be x squared, it could be 5. So the cross-sectional area here is important, so we're going to name that a of x, and it turns out to be pi f of x squared. So if I want to find volume, I'm going to integrate from a to b of my cross-sectional area with respect to x. So this a of x in this example becomes, so this is in general, but for this example, my volume is going to be the integral from a to b of pi f of x squared dx. Does everyone see that? The cross-sectional area, these slices are slices along the x-axis, or perpendicular to the x-axis.
Yeah, they're like y slices.
I wouldn't say they're Y slices. The slices are parallel to the Y-axis. So yeah, they're parallel to the Y-axis, so perpendicular to the X-axis. So if I take a slice perpendicular to the X-axis, my differential length is delta X. So if I take an area times the length, I get volume. Just like in chapter 6.1, if I took a height times the length, I get area. So if I integrate an area function over an interval, I get volume. Does that make sense? So this is the disk method. So let's look at the example of the washer method, which will be very similar to finding area between two curves. So if I draw a picture here, f of x, let's name this one g of x. So this is the x-axis, this is the y-axis. If I come in here and rotate it about the x-axis, you see that I have this cylinder that has a hole in the middle of it. So I don't know if I should even attempt to draw this. So if I take this and rotate this, I prefer to draw just the cross-sectional area because that's all you need. So if I'm rotating this about the x-axis, then if I take a slice out and I come over here to see what a cross-sectional, I always draw the axis of rotation because that gives me a reference point. And then I come in here and I'm going to have a washer. And I have some differential length here on these washers because they're volumes. So this differential length would represent dx. So hopefully with repetition here, you're getting the idea that I have the x-axis, I have dx, I better have functions of x. And we'll see example when we go to y, how sometimes reminding yourself this is important. So what is going to be the cross-sectional area of this shape?
Yeah, the big one minus the middle.
Yeah, exactly. So if I take, what is the radius from the axis of rotation to the outsidemost function? It's going to be this distance, right? How would I write this distance from the axis of rotation to? It's just f of x, right? And then what would be the distance of my axis of rotation to my inside function? G of x. So what is going to be the area of this cross-section? Pi times f of x squared minus pi times g of x squared. And of course I could write that as pi times f of x squared minus g of x squared. Oops, sorry about that, guys. Does that make sense? I take the pi times the outsidemost function minus pi times the insidemost function. That gives me area of the cross-section. To get volume, I multiply that by my differential, right? And then if I add up all those volumes from A to B, I'm going to get the volume of the whole shape. So the volume here would be the integral from A to B of pi f of x squared minus g of x squared dx.
How are you getting these shapes?
This shape,
Yeah, like how are you folding that to get?
if I take a rectangle and I rotate it about the x-axis, I get a washer. So that's a good question. Let's go to Wiley. Wiley has applets. Honestly, in the 10th edition, the applets were quite a bit downgraded from the 9th edition. So I'm going to pull up the 9th edition applet, and I think we'll be able to see this a little easier. So we're going to look at the applets from this section. Okay. So you see I have an area bounded by two curves. Then if I come in here and I rotate this about the x-axis, I'm going to get this shape. Does everyone see the shape? So that's kind of what I'm trying to find the volume of. But doing that, what I'm really doing is I'm just rotating a slice of that. And each slice is going to look, anytime I'm rotating something, it's going to be circular. It's either going to be a washer, where I have a solid shape. So if I look at this value of the function, the very first cross section is a washer. So if I look at the area of, a disk. If I look at the area of a disk, it's just pi r squared. If I want to find the area of a washer, it's going to be pi, the outside radius squared, minus pi, the inside radius squared. But once I have that function, I integrate that function along my bounds, and it's going to give me volume. Because if you integrate area on a bounds, that gives you volume. If you integrate height on a bounds, that gives you area. Question?
So the integral of the function is the radius.
The integral of the cross-sectional area on the bounds is the volume.
Well,
the height.
To get the volume, you take the area of the circle, right, is pi r squared.
Mhm.
So you're saying that the function, or the integral of the function, which is the squared, that's the radius.
The function squared is the radius.
Yes.
Or sorry, the function is the radius. So do you see that this radius is changing? From 0 to 2, the radius is changing.
That's why it's the integral, because it's changing. It's not a constant.
The reason it's changing, so it's a function of x. So the height of this is a function of x. So the radius of your radius of a cross section is going to be a function of x. Then you integrate that function of x on your x bounds, and that will give you volume. Question?
Okay, I don't mean any disrespect by this at all, but what is the point of all this?
So this is used a lot of applications in like machine design. So if I need to design this part, I can go in there and take a solid piece of plastic, and then I might take a shape that I want to design out, and I'm going to say, okay, I'm going to take this shape, and then I'm going to cut it in this plastic, and I'm going to rotate it 360 degrees. I'm going to get this shape. So I might want to I want to maximize my volume or minimize my volume and type of things of the block of plastic that I have. So a lot of things can be made this way. Dog bowls are an example of something that I think is designed this way. Another thing in engineering, because I know a lot of applications in engineering, does anything ever do anything in like AutoCAD where you have to draw things? So SolidWorks or InDesign, Inventor. If you have an idea of this shape, then you can rotate it 360 degrees and you have a three-dimensional shape. So if you're designing a machine, you can get all these parts and then you can look at them in 3 dimensions. Volume. There's some applications in probability and statistics when you want to look at a sample space or something, and you can use integration techniques.
Have you heard of those machines that apparently they're coming out with where you can just put in, like, I guess a picture and then...
3-dimensional modeling?
Yeah.
Yeah. So it's a 3-dimensional printer
The engineering department has one.
that you could, so it actually builds things in 3 dimensions. I don't know if this would be the exact correlation towards that, but the idea of eventually, if you want to find volume of anything, all you have to do is take a cross-sectional area. So if it's some function, you take a cross-sectional area and find the area of that cross-section and integrate that from your bound. So I don't...
the bounding of the whole thing by doing that, but...
So let's look at an example. I'm going to go ahead and pull up the book real quick.
Good thing I'm not building anything. I'm not sure.
Let's pull up the book because the book has some nice some nice pictures here. So this is an example of, of shape that if I want to get some kind of bell curve, I take this shape and I rotate it about the x-axis. If I want to find the volume of this, I don't have any formulas for a volume of a bell curve. So what I can do is I can take a cross-sectional area. So every cross-section of this is going to look like a circle. So it's going to be a function of x, though. So the height of this is going to be, the radius of this is going to be whatever x is at that point. So if this was x squared, then when x is 2, the height is 4. If x is 3, the height is 9. So I can just represent it as x squared, and the calculus will take that into account. And if I integrate that from a to b, if I add up each individual area from a to b, I'm going to get volume. And so that's the power of the calculus. So we did a couple examples in terms of the x-axis. Rotating a function with respect to the x-axis. Here, I get a hollow bell. So to find the cross-section, it's going to be the pi times the outside radius minus pi times the inside radius. That's going to give me the area of a slice. And then if I integrate from A to B of the cross-sectional area, I get volume. Question?
So that little piece that you're doing is going to give you the whole thing?
When I integrate it. So this little piece that I do will give me the area of that little piece.
Right.
When I take that area times the differential length, I get volume, right? So then if I add up each individual volume from A to B, I get the volume of the whole thing. So the integral of the area with respect to the x-axis from A to B gives you volume. Just like in 6.1, where we took the height times the differential length from A to B give you area. So now you need to come up with this cross-sectional area function. Integrate that area function on your bounds, that will give you volume. Did someone else have their hand?
Yeah, I'm just confused about that little section.
This little empty hole,
No, the
cross-section, how do we get this?
I just don't understand, why can't you just take it from A to B? I don't,
Take what from A to B? The
the
function?
area,
But how do you get area?
by figuring out the area of the first one minus areas.
That would give you height. Right? If I take the height of the first one minus the height of the second one, that would just give me a length. To find area,
That's what I'm saying, so you take the volume, just like you were doing, what's the point of the line?
this line, this line just tells you that I'm taking a cross-sectional area. This line is to represent that this cross-sectional area is actually a washer. See, I'm rotating this about the x-axis. To find area of this, I integrate from a to b of f of x minus g of x. That gives me area of this shape. To find volume, I need to integrate the area of each slice. And the area of a slice is going to be a disk.
But isn't it like impossible to add all those little things up? So it'd be like infinite amount?
It is infinite amount, and that's where the series comes in with the integration, right? So if I were to divide this up into 3 washers, then I'm going to get an approximation. But if I take the limit as the number of washers goes to infinity, that summation changes into an integral.
Yeah, that's just like what we did on the area.
Exactly. It's
Now
the
it's
exact
in
same.
one dimension.
Now we're in 3 dimensions. Yeah. So let's look at a few more pictures. Your book does this example where we have 1/2 plus x squared. So that's the top curve. And we have y equals x, which is just the line. It's the bottom curve. When I rotate that about the x-axis, each slice is going to be a washer. So the height from the x-axis to the outsidemost function is 1/2 x squared. So to find the area, I take pi times this function squared minus pi times this function squared. And that's exactly what they're doing here. Pi times this function squared minus, and the pi is out front, this function squared. So they went ahead and squared it, simplified like terms, and then they came through with this idea. And a lot of times in this example, your answer is going to have pi in it because it always has to do with rotation. Question?
So when do we know when we are using the washer or the disc?
Depending on the function. So here you see when I rotate this, I have a hole. So I'm going to have a washer. If I do an example...
You're saying the space between the x-axis is your hole.
Or your axis of rotation.
Okay.
So we've been focusing on the x-axis, but we can do the exact same thing in terms of the y-axis. So our cross sections are going to be perpendicular to the y-axis, so our differential length is dy. And we're going to integrate from c to d, so we need to make sure our function is a function of y. But here this is going to be a disk, right? Because the shaded area touches our axis of rotation. So we have a full disk. If we have a function like this, where our shaded area does not touch our axis of rotation, we're going to have a washer. So we're going to integrate along the dy from c to d. So the same concept, it's pi times the outside function minus pi times the inside function. But the most important concept in this example is that you're getting a function of y, dy from c to d. So that's kind of the trick on these, or the setup. So let's look at some examples from the written homework. So let's look at number 1. Let me get back to the 10th edition.
And you're subtracting that inside function because it's like hollow.
It's hollow,
Fold it in,
exactly.
right?
Yes, because you take, if you did the outside, pi times the outside function squared, that would give you a solid shape.
Sure.
But then if you do the inside function, that gives the same concept as when you're looking for area, you take f of x minus g of x, because f of x would be this whole area, and g of x would be this area, so when you subtract it, you just get that area. So the same concept there. Question?
For the integral function itself, because pi is out front of all of it, you can pull pi out, integrate it, and then put pi back in?
Yes. Pull out pi, because it's just a constant. Question?
If it's like touching the x-axis, though, like at 0, then it's not hollow, right?
Correct.
It's just a sphere. So what are you doing then? You're not
So you can still subtract it, but at that point you're subtracting 0. So an example, you just take for an account that it's a disk, and at that point the calculus will take part that it's a washer. The calculus will take part that it's a disk for the first 4 or 5 x values, and then it goes to a washer. And so once you get that set up, the calculus will take that.
Will there be shapes so that it's not a washer ever? Like,
yeah, and that would be like a disk all the time.
okay, so like g of x would always
Be 0. So you would take pi times f of x minus pi times 0 squared, which is always 0. So that's going to be this first example we look at, number 1. Would everyone be able to agree that you could see that this is always a disk? It's going to be a solid shape, right? So let's look at so this would be y equals the cube or the square root of 3 minus x, and I want to find that from minus 1 to 3. That's being rotated about the x-axis. So we hope to get 8 pi, and we can see the answer right there. But more important in this section is the setup, because what I'm envisioning on the exam 4 is a problem that says setup but do not evaluate, because we only have 50 minutes. I will test you separately if you can evaluate an integral. In this section, I want to focus on, can you set it up? If you can set it up correctly, I hope your calculus is strong enough to evaluate it. So if I rotate this, I take a cross-sectional area. I like to always come over here and draw my axis of rotation. That will tell me if my slices are perpendicular. My slices are always perpendicular to the axis of rotation. So that just reminds me, I'm going to come in here, I have this disk, so I have some differential length, and I get this differential length is along the x-axis. So hopefully by writing this a couple times, by the time I get to pick out the height, I always make sure that my function is going to be the function of my axis of rotation and my differential length. So what is the distance from my axis of rotation to the function in terms of x? This distance is changing, right? At this point, it's 2. At this point, my distance is 0. So it's a function of x, which is the square root of 3 minus x. Does everyone see where that comes from? You have to be really, really careful when you're integrating along the y-axis because you need to make sure your function is a function of y. So you might need to rewrite something. We'll see an example of that. So what is my area of this cross-sectional length? Pi. Right? So this is a cross-sectional area. If I integrate this cross-sectional area along the x-axis, dx, I get volume. So the volume is going to be the integral from minus 1 to 3 of pi times 3 minus x dx. So I can write that as pi times the integral from minus 1 to 3 of 3 minus x dx. And this is really kind of where, well, the square root of a square cancels, right? So this is a very elementary integration problem once I get to this point. What I want you to focus on is being able to set this up correctly.
And we're going to be given all that in.
You'll be given the picture. Or you'll be given the function and expect to graph it.
And will our bounds be there?
Yes. Or it will be find the volume from minus 1 to 3 of this shape.
So we might have to graph one?
You might have to.
We don't know exactly how to get the final answer to this problem.
Well, you should know, right? Because this is just an integration.
What about all the different little sections?
That's done. And so you say the algebra is adding up the sections. And the power of calculus is saying that is what you're doing. Is you're integrating this cross-sectional area over an interval that gives you volume.
Well, what if there's like a peak in the middle of
The calculus will take care of all of it.
all of it?
Yes. That's why it's so powerful. This is the fundamental theorem of calculus. Algebra would be a mess, right? Algebra, you would have to divide this up into subintervals and say, okay, let's say we divide it up into 10 subintervals. So then I find the radius here, and I multiply that by pi squared, add it to the radius here, multiply it by pi squared, pi times the radius squared. Do that infinitely times. Then you're only going to get an approximation value. You won't get an exact value.
You divide by the number of times you did that, right?
You wouldn't divide by the number of times you do that. You would just add them all together because when you divide it up here, you only get an area approximation here. It's the same thing with what we did here, right? If I take the height here and I add them all together times some differential length, if I take the height times the length, I get area. If I add up all those individual areas, I'm going to get the total area. Same thing here. That this height times some length is going to give me volume. Sorry, this area, which would be pi r squared, times some differential thickness would give me volume. If I add up each one of those individual thicknesses, I get the volume.
So in a disk, is the radius always going to be the y that's given, the function of y?
If you're integrating along the x-axis, it's a function, the y equals a function of x. If tomorrow we'll do an example where we integrate along the y-axis, we need to make sure we rewrite our function in terms of y. So we need to solve for x. And then that would be our y distance of our radius. You would the y.
And you can just.
Yeah, so